So the paper is entitled Mind Your Path on Key Dependencies in Differential Characteristics. The paper is by Thomas Perrin and Quan Quentin. Okay, and I think we are ready to start. And Quan Quentin is presenting the paper.
Okay. Thank you for the introduction. So once again, my name is Quan, and the title of this talk is actually Mind Your Path on Key Dependencies in Differential Characteristics. And this is a joint work with Thomas Perrin, and we are from Nanyang Technological University, Singapore. So actually, before we go into the details of the paper itself, let's go through some preliminaries. And since this is just the second talk of this conference, we will start off easy, and we will start off with like what's the basics of differential cryptanalysis in general. So for cryptanalysis in general, what we really want is that, let's say we have a keyed function or a cipher. We want to actually recover the key for a key recovery attack to get for a particular plain text to the cipher text itself. So how we actually do it is that we usually want to find a distinguisher that covers the majority of the rounds. And then afterwards, at the front and the back, we can add a key recovery round, which will actually let us to recover the key. So for differential characteristics, differential cryptanalysis itself, what we really want is that a distinguisher that have a probability of a certain delta in, a difference in the input, leads to a difference in the output, delta out. And in order for the key recovery attack to actually perform, we usually look for a distinguisher with a probability that's pretty high. So note that actually, even though we have the maximum of the probability of distinguisher, doesn't really mean that the key recovery is the best, but at least it gives us a rough gauge of like how the distinguish, how prone or susceptible the cipher is to differential cryptanalysis. So now we have two questions over here. The first one is that how do you actually find a delta in and delta out that guarantees a good probability for the distinguisher? And the second thing is that how do we actually find the probability of the distinguisher itself? So if you break down the ciphers into many portions, what we can see is that actually the probability is a summation of a lot of paths. So note that I actually lift out the values over there. So actually in the actual case, it actually depends on values and everything. So this is made out of a lot of different paths. But the thing is, in reality, we would not be able to actually exhaustively search for all the paths. So most of the time, what we will do is that we just look at one of the dominant differential characteristics. So we just evaluate the one of the path itself. And usually what we do is that we look at this differential characteristic and we have a rough gauge of like how good the differential is, or at the very least, it gives a lower bound on the probability of the distinguisher. So now the question will become, how do we actually compute the probability? So for this, we have to rely on the other assumption, which is the Markov Cipher assumption, which states that the differential probability of the round function will be independent of the value. That's assuming if the subkey that's input to the round function is actually uniformly random. So under this assumption, what we can do is that we can split this probability into a product of probabilities, assuming they are all independent. So once we know that we can evaluate the probabilities round by round, the next thing is that we can actually use a lot of the tools that we actually know, such as the DDT or like automated methods, to actually find a good delta in and delta out for the distinguisher itself. So now the question is the Markov Cipher assumption actually valid? So for this, we have to look at the premise of the assumption itself, which is that we have to make sure that the subkey is uniformly random. But in actual reality, when we perform like key recovery attacks, the key is often fixed. So this means that actually the value of a certain round actually depends on the value of the previous rounds. So this is actually noted in a lot of the papers previously. So for example, when you deal with like permutations or hash functions, they do not have any key input, or you can treat them as like a key of like all zeros. So in these cases, actually for the characteristics, they might not actually work at all. And also for the Feistel networks and everything, so Canto et al. In FSC 2017 also do an in-depth analysis on like Feistel network for 3 rounds and finding the exact probability. And in DCC 2020 and Liu et al. Also introduced singular characteristics. So these are the characteristics that actually work in terms of based on all the assumptions that we have, but in reality, there are no keys that actually allow this characteristic to pass. So later on, we actually look at one of the cases of a singular characteristic as well. So for the case of LVD, the analysis will be extremely careful, because of the step function, which is essentially a 4-round AES-like cipher. 4-round AES round function. But the thing is, for each of the each of the 4 rounds, within itself, there's only addition of round constants instead of like a key. So also on ARX ciphers, there are also many works that they are developing tools to actually find out like whether a characteristic is it valid or not, or like to improve the correctness of the characteristics. So we will now look at like the round function of Skinny. So Skinny is a trickle block cipher, and the block size is either 64 bits or 128 bit. So it actually follows a structure of similar to like what AES is doing. So each of the cell is actually either a nibble or a byte. So for the tweak key size itself, it's either 1 time, 2 time, or 3 time the size of the block size, also known as the TK1, TK2, and TK3 version. So one thing to note is the key schedule over here. So the key schedule is rather simple. For each of the TK1, TK2, TK3, there will be a permutation. So this is just a transposition of like the cells. And then within each cell itself, there will be an LFSR for half of the states. So 8 nibbles or 8 bytes having an LFSR after each round. So now we'll look at the motivation for this paper itself. So what we want to do is actually to find out what actually goes on underneath all these dependencies on the keys. And ideally, we want to find out all the possible constraints and lead to the necessary conditions on the key. So when the dependencies are not too complex, which generally when a characteristic is not so dense or the probability is pretty good, is the case, you want to actually know the size of the key space, as well as the probability distribution of the characteristic itself. The next thing is we want the search method that actually allows us to actually incorporate all these constraints that we'll be talking afterwards, so that we can actually find characteristics that avoid having this singular characteristics components. So we'll look at an example of Skinny. So on top, you'll see a round function, a round of Skinny itself. So note that the cells highlighted are actually the cells that we are interested in for this case. So we will focus on the yellow highlighted cells. So once we have taken out from the round function, it's on the bottom left over there. What we can see is that, okay, so note for the numbers inside the cells itself is actually the differences. So what we can see is that based on the differences and everything, we can deduce what are the values that are required at the particular input or output of the S box. So in this case, what we will look at is the transition from D to 2. There are only 4 values allowed, as well as from 2 to 5, there are only 4 values allowed. So in this case, we can actually deduce that what are the keys that will actually allow this propagation to go through. We can also do the same thing for the ones in the pink as well. So in this case, what we can see is that the key cell that's involved in both constraints are actually the same. So in this case, what we have to do is to get the intersection of it and see how many keys are actually allowing these 2 constraints to pass. So in this case, you can see that the intersection has nothing over there, which means that actually for this particular round, there won't be any keys that allow this characteristic to pass through. And this is also a type of singular characteristic. So we call this kind of constraints the linear constraints, mainly because they do not actually involve any S boxes in the middle, but it's just the output or the input of the S box itself. The other type of constraints that we call the nonlinear constraints. So these are the constraints that actually involve a inactive S box, as you can see highlighted in green over there. So these constraints are often being ignored because even though over here is inactive, but it doesn't mean that the values are, you can choose any values that you want. Usually this kind of constraints arise when you have some sort of cancellations happen before that. So in this case, you can see that after the propagation from 2 to 5 for both cells, they actually cancel off and the difference is actually 0. So for this kind of constraints, the constraints on the key itself is a little bit more complicated because there are two keys involved and it's a non-linear interaction. So what we can do is to list down all the tuples that we have over here. So the next kind of constraints is the higher order constraints. So basically for this kind of cases, what we have over here is that we have 2 or more output values output cells instead of the previous one where we always stick with just one output cell. So in this kind of constraints for skinny especially, it can involve the key or it may not involve the key at all. So in this case, you can see that actually the X and the key itself is involved in 2 constraints. So once you actually combine them together, the key doesn't really matter anymore. And what happens is just the values that are in play. So once we have identified all the constraints via an algorithm and everything, the next thing is that we want to actually compute, like how does this constraints actually change the key space as well as the probability distribution. So ideally, what we want to do is that we want to take all these constraints and evaluate them at one go. But usually, when the characteristic is long, we have a lot of constraints, and it's really hard to actually evaluate them all together. So what we have to do is to break them into groups and ideally hope that these groups are actually independent of each other and we can compute the probability individually. So these are the conditions that we actually use to group them together. So first of all, if they sell one key cell together up to the key schedule, so note that the skinny key schedule is actually pretty simple. So each of the neighbor or the bytes actually stay within itself and they will not mix with other neighbors or bytes. The next thing is that if they also share one S box together, so one of values that so for example, one constraint, the output is the input of the next constraint, then these 2 constraints will be together in the same group. So of course, after we dividing all these groups and everything, there might be a chance that it is still too huge for us to actually compute. So when the groups are small enough, we can actually just straight away compute the change in the probability. But let's say if the groups are slightly larger, what we can do is to further optimizing it. So note that for skinny itself, there are TK2 and TK3 versions. So this means that actually, so note that when you find the key constraints, the constraints on the key are the ones that after you XOR together. But the thing is, once you actually expand it out to a TK2 or TK3 version, it's actually a higher, there's actually more dimensions to play with. So for example, let's say if the key 4 is not allowed in a particular round n-1, after you expand it out into the TK2 or TK3 version, and you pass through an LFSR, actually it actually split the impossible key into like all the other values. This is also thanks to the LFSR itself. So essentially, let's say you have 2 constraints on 2 different rounds, working on the same key, they will interact in the uniform way such that like the probability can be split. So the next thing is that let's say if we have within a group itself, there are 2 constraints that actually only have one S box overlapping. So what we can do is that we can split these 2 constraints into 2 different groups and we evaluate the probability sequentially. So we evaluate the top first, and then based on the values that are allowed for the first constraint, we apply it to the second constraint. So we only split the group when there's only one S box in common, because if there are two or more S boxes in play, there might be some correlations that are preventing the values from appearing. So once again, if let's say after these optimizations, we still cannot evaluate it theoretically, we can do an experimental search. So this is a summary of the results for Skinny. I don't put a table over here because it's pretty huge and messy. So out of the 21 tested differential characteristics that we have, we realized that actually 10 of them are actually impossible or singular characteristics. And for the remaining differential characteristics, they actually only work for a small key space. And for Skinny 64 itself, we can actually plot the estimated theoretical probability distribution. So this is one of the example. In the table itself is what we actually compute, and the graph actually shows what we actually do experimentally. So this is on, if I remember correctly, about 4 rounds of a particular characteristic, so that the probability actually stays in what we can actually compute experimentally. So for Skinny 128, we tested about 22 differential characteristics, and 11 of them are actually impossible. And once again, the rest of the differential characteristics also have some sort of constraints on the key space. And for this, for most of them, we actually require an experimentally determined probability distribution. So actually, once we split into different groups, some of the groups that are small enough, we still evaluate it theoretically. But for the ones that are too large, we will use the experimental approach. So we can actually do the same thing for GIF itself. But for GIF, because of the interactions of the bit permutations, for the nonlinear constraints, we cannot actually go for far too long. So for both versions of the GIF, out of the 15 tested differential characteristics, one of them is actually impossible. And for the one that we actually tested for the impossible case, it's actually not due to a key constraint. Because if you recall for GIF itself, not all the bit permutations actually involve the key bits. Some of them do not involve the key bits. So for this impossible case, it actually involves one that doesn't really add in any key or wrong constants, which means that even if you change the key or you change the wrong constant, this characteristic doesn't really work. So most of the remaining tested differential characteristics also have some key-dependent constraints. Okay, so let's go back to the question at the start, which is that what we're looking for is actually differentials. But for this work itself, we actually focus mostly on differential characteristics. So over here, even though we show that a differential characteristic is not valid, it doesn't really mean that the differential or the boomerang or rectangle is actually impossible. So like for most of the results that we actually showed just now, most of them are taken from like some boomerangs or rectangle or like differential usage. So in those cases, the results are still validate, provided they actually do an experimental out. So over here, what we want to do is to warn when it comes to like theoretically computing like a key recovery attack, it might have some errors inside there. So one thing to note is that actually because the one that we're looking for is actually a dominant characteristic, which means that if it's not working, that means the probability of dominant characteristic may change. And this may also affect the probability of differential as well. So we have done some experiments and to look at like differential in the case of differentials, whether they are actually valid or not. So we actually tested 2 cases, and just happens that one of them actually works. That means there are some other characteristics inside the differential that allows the inputs to pass through. But in the other case, there's also a possibility that actually there are no valid keys that allow any of the characteristics in the differential to pass through. So this is actually very subjective to the round function, how is it being constructed, as well as to a certain extent, how many trails are there in the differential. So of course, if you have more trails inside a differential, there are higher chances that one of them will work. So lastly, what we want to do is to actually integrate with like automated methods and everything. So previously, most of the searchers that overcome this kind of issues, they focus on finding a right pair directly for the to ensure that the characteristic actually works. However, this may actually have a very high complexity in terms of like the search space and everything, because they have to actually consider actual values and everything. So over here, what we are trying to do is actually try to incorporate the constraints that we actually found into CP. So previously I talked about like the linear constraints, nonlinear constraints, and the higher order constraints. What we do is that we try to incorporate the linear constraints inside. So to a certain extent, it it helps to avoid most of the incompatibilities that arise due to the linear constraints, but we some sort ignore the rest for the time being because we do not want to increase the amount of like variables in CP itself. So yes, so what we do is that we actually manage to, so for one of the impossible differential characteristics that we found previously, we put inside the CP itself and we input the constraints that allows to change the parts that are having issues. And what we eventually get is a particular characteristic that actually is correct. So what we do is that we actually evaluate it experimentally and it actually works. Yep. So that's the end of my presentation. Thank you for your attention.
Thank you very much. Any question or comment? Yes.
Thank you very much for the talk. So you find some constraint so that in differential propagations, but how to find these constraints, and so is it so sufficient or something there is a possibilities overlook some constraint? So is it so actually I think so that there are many kinds of the constraints and the non-linear, linear, and but many constraints. Is it enough?
Okay, so this is a problem that we actually struggled with as well. We cannot really guarantee that all the constraints that we have found are the constraints that we that exist. But so what we did is that we look at all the small characteristics and we actually plot out experimentally as well as the theoretical values. So they actually match. So at least for small characteristics, we can say that most of the dependencies we actually find out. But for larger characteristics that we cannot really test out experimentally, we cannot say for sure.
Okay, thank you very much.
Thank you. Over some other questions here in the room? Or maybe in Beijing? Do you have any question or comments to the speaker in Beijing? I think we do not have any question in the chat. No.
Dr. Tan, excuse me?
Yes. Yes, we can hear you. Yes.
Dr. Tan, I noticed that there is a difference between your theory and your random experience, and I am a little curious about how you look at this difference, and maybe in another word, maybe your how I want to know how do you look at it, and the reason, or maybe you can you explain the reason why it would be happen? Can you get it?
The question, as far as I understand, is that there are some differences between your the theory that you presented and the experiments. And how can you explain that between the difference with the experimental results?
May I know which experiment are you referring to?
Just like in about page 20. The pictures and the list.
This one?
Yes. In your list, there are about 6 values and the corresponding percentage. But in your figure, there are some other values and probabilities. I am a little curious about this. About the reason why it would be happening.
Sorry, I didn't get what you're asking.
In your list, there are 6 values in your probabilities.
Yes.
Yes, and in your picture, there are some other values. Do not fall into the list.
Ah. Actually, there are only 6 values inside there. So you can, as you can see, this is some sort of like, because experimentally there will be some sort of like probability will spread throughout. So what we should be looking for is the parts that are slightly horizontal. So what you should be focusing is, can you see my cursor?
Yes, I can see it.
Oh, you can see, okay. Yeah, so what you can see is the ones over here. This is the second one, the third, the fourth, fifth, and the sixth. So the rest are due to experimental errors and everything, but what we can see is that there is a distribution over there that, yeah.
Okay, thanks for your answer.
Thank you. So I think we don't have any questions in the chat. Okay, so I guess we'll stop here. So thank you. Thanks very much. And let's thank the speakers, also both speakers that we have in the session. Thank you.